So I'm the host. So today we have 1, 2, 3, 4. Only 5 of you are there. Just let me share my screen. Right. So people, I think we have completed your carbons compounds, right? Homologous series was the last one we saw, if you can remember, right? So only one chapter is left, right, for you, and that is periodic table, right? So guys, can you tell me what are the deleted portions in periodic table? What portions are deleted in periodic table? Can you tell me, or what is only there? You can tell me. People, are you there?
So 1 second, sir.
Okay, okay. Okay, something is there in the chat. A period classification need early attempts, Dominus triads. Okay, fine. I think no portions are deleted. All the things that are there in this chapter are there for you. No portions are almost deleted. Okay, fine. So moving on. I mean, today we'll start with a new chapter. All right. Okay. So people, right? So this is again going to be a very interesting chapter. All right. Okay. So what are we going to study in this chapter? Right. In some of your schools, this chapter would have been started, and some of your schools would have been completed. Right. But we have to understand what are we going to study in this chapter first, right? So people, we know that maybe from your ninth class, right? From your ninth class, you would have understood that matter, right, can be classified into two main categories, right? First one is what is called as pure substances, right? And the other one are what are called as mixtures, right? So the first one are what are called as pure substances, right? And the other one are what are called as mixtures. Like you might have studied this classification in this chapter called as is matter around as pure. I don't know how much you remember, right? So that would have been your second chapter in chemistry in your ninth class, right? Okay, so we say that we know what is matter. Matter is anything which has mass and occupies space, right? Anything which has mass and volume is what is called as matter, right? So any matter, as I told you, will be able to classify into two types. One is what is called as pure substances, right? The other one is what is called as mixtures. All right. So what are these? What is pure substances? These pure substances are made up of single entities, right? They're made up of only one. They're made up of one type of something. Okay. Only if you check, only that type of particular substance is going to be there, right? That's why we say it is made up of single entities, right? Okay. Now these mixtures are made by combining pure substances, right? So if you take two pure substances and you mix them together, right? Now that is going to become a mixture. And obviously they are going to be made up of more than one entity. Here in the case of pure substances, they are single entities. So two single entity molecules, two single entity substances will be mixed together, and that's how you get a mixture. All right, fine. So now based on what is the single entity, right? Based on what type of entities are we talking about, right? I will be able to further classify them into two types. Your pure substances can be further classified into two types based on what is the single entity, right? Now, they can be further classified into elements and compounds, right? They can be further classified into elements and compounds. All right. So you can understand that elements are going to be made up of only one single entity called as atoms. Is it not? That's very simple. Say if I take, for example, sodium element or say chlorine element, they'll be made up of sodium atoms only, and chlorine element will be made up of chlorine atoms only one entity, right? Only one single entities are there. So we can tell based on, based on the fact that the single entity can be atoms, and those pure substances are what are going to be called as elements, right? And obviously, in case of compounds, right, the single entity which we're talking about is going to be molecules. Right? Say in the compound of H2O, if you take H2O, for example, the compound, right, it is going to be made up of molecules of H2O. Carbon dioxide gas is going to be made up of carbon dioxide molecules. We know what is the difference between atom and molecule. Is it not? Two or more atoms combined together to form a molecule. A molecule is say a combination of two or more atoms. Isn't it? Same way, I'll be able to define the compounds also. Two or more elements combined together to form compounds. Is it not? Say carbon element, oxygen element will combine together to form a CO2 compound, right? So we understand, it's very simple to understand, isn't it? So people, right? So we understand that these pure substances can be further classified into elements and compounds, right? Like if you, I can even go to this part, mixtures. Mixtures can be further classified into homogeneous mixture, heterogeneous mixture. We don't have to go into the details now, right? You might have already gone through all of these in your chapter. That chapter is Marathon pure, right? So we are going to lay our interest upon this particular thing in this chapter, right? Elements, right? So we understand that elements are going to be made out of atoms, right? Those are the single entities we're talking about. I would say those are the elementary particles. I can even call it like this. These atoms are your elementary particles in the case of your elements. Right? Okay. So keeping all this in mind, right? Now we understand that elements are going to be fundamental things of any compound formation. Is it not? If you have to combine these elements in the proper ratios, you have to combine these elements in proper conditions to form compounds. Right? So it is very much required that we have to study elements. Right? We have to study about the elements. They have to study about their properties. We have to know anything, and like we have to know everything about a particular element, right? And then only you can talk about, okay, if I know about this element, another element is there, how will they react together, right? So, or say if I now based on how they react together, now I can form compound. Now based on the properties of the elements present in the compound, the property of the compound also will change, right? Say for example, we have H2O. We have H2S, something like this, right? So here oxygen and hydrogen combine, here sulfur and hydrogen combine. Now you understand that they are actually forming same kind of species, right? H2X, right? So you understand that oxygen and sulfur actually show similar kind of reactivity towards hydrogen, because that is why they're forming similar kind of compounds. Is it not? H2O, H2S, right? And say you can compare another thing also, say NaCl, KCl, sodium chloride, potassium chloride. Now again, you see the type of compound formed between sodium and chlorine, between potassium and chlorine, again are going to be similar. This is like some AB type of molecules, right? Right. So we have to understand why is it that certain elements are going to form certain similar types of compounds, right? And again, that is going to depend upon their properties, right? So what I'm trying to say is, people, right? Every element will have their own kind of properties, physical properties, how they look, how they appear, what is their strength, what is their this thing and all that, physical properties, and like this, how they react with some other element, right? So that is what is called as chemical properties. Right? So if at all you want to know about the physical properties and chemical properties, you have to take the individual element, right? One element you have to take and study them properly. Is it not? Right? But since these kind of elements, like say sodium chloride, potassium chloride, H2O, H2S, something like that, you understand that certain elements form similar compounds, right? So if I can actually somehow group these elements together, right? If I can just somehow make a group of elements, say group 1, group 2, group 3, group 4, right? Now the elements that are going to come in that particular group, I can tell that they're going to have same properties, right? So we are going for grouping, right? We are going for grouping, right? Now what is the whole advantage of grouping? Say for example, if I know about sodium, right? I don't have to fully investigate about potassium, because they are going to be they're going to have similar properties. right? If at all sodium forms sodium chloride, K will form KCl only, we'll be able to predict. Say if at all new element is found out, and if that new element is found out to be in the group of sodium and potassium, say that element was some X. Okay, now we know for sure how it will react with chlorine to form a compound. We know it is going to form a compound like XCl. Right? So the advantage of grouping is that if at all you're able to group elements, some elements together, right, you will be able to study them easily. Okay, you will be able to study the properties of these elements in a little more efficient way, right? Okay, now because there are, now you will understand that now on chemistry we have almost 118 elements, right? We have some 118 elements in the period, like the modern periodic table, which we'll study later, right? So it is not possible for us to take each and every element and study their properties. It is going to become very difficult. It is going to become very tedious, right? So to avoid all these things, right, so all these elements are going to be grouped into certain groups, right? Now by that way we'll be able to study them better, right? And we'll also be able to predict if at all a new element is discovered, right? If at all a new element is discovered, maybe now, not now, from earlier times, like say in 1800s, right? In 1800s, only some 40 elements were known, not even 40 elements, 20 elements were only known, right? So in some 1850, something like that, some 70 elements were known, something like that, right? So what your understanding is, as time passes by, right, as we move along in the future, more and more elements are actually going to be discovered. Okay, so before even they get discovered, right, we'll be able to predict, okay, if at all this is discovered, if at all you find an element or whatever name, right, it is actually going to have properties similar to this group, right? So all those things become more and more efficient if I go for classification. The classification is nothing but grouping, right? Grouping is nothing but classification. What is classification? Dividing them into groups. Okay, this group will react with chlorine like this only. This group will react with chlorine like this only, right? So some other group will react in a different way, right? But all the elements in that particular group will react similarly, right? So that is why we go for classification. Like, see, the easiest way to, I'll tell you, one of the easiest way to classify elements, right? Dalton did this. Right, Dalton actually was the first element actually to, whatever was the elements known at this time. Not many elements were known, 108 elements, very few elements were known at that time. Okay, now he did the classification like this. He classified elements based on, say, whether they are solids, and whether they are liquids, right, or whether they are gases. Right. So again, what are we trying to do? We are again, see, these are the same properties now. Whatever is going to be in this particular grouping, solids, all of them will be in solid state, and obviously liquid state, and all the things are going to be in this particular group are going to be in gaseous phase. Right. So this is what is classification, right? Dividing elements based on their similar properties. Right. But again, this was a very bad way of doing, because not all solids. Now this is physical properties. Okay, solids, liquids, and gases. Right, but among solids itself, I will have different properties. Some solids can be very soft, some solids can be very hard, right? And say, for example, liquids, if I say some liquids will have very less viscosity, the other liquids will have very high viscosity, right? Some other things, maybe say gases, some gas can be very heavy gas, very high dense gas. It can be, or it can be a very, less dense gas. It can be a lighter gas. Right, so among solids, liquids itself, you are able to classify, and among them, like into, again, they can be further classified into some other groups also, but that means that is not an efficient way, right? Just by classifying them into solids, liquids, and gases is not enough for us to study them efficiently. Okay, right? So various efforts were made for classifying these elements based on their properties. Okay, so many scientists attempted it. Okay, so we are going to see the history of how these elements were classified, right? What are the basis for this classification, and how, obviously, we're going to see the history, means older stuff we are going to see, right? And we are going to see how we move on to the modern periodic table. Right? We are going to see how in 2020, in the 20th century, right? How are you going to classify elements? That also we are going to see. Obviously, there were some problems. Okay, there were some problems which were there in the previous classification, in the previous ways of classification, right? So that's the reason why we actually go for that's the reason why we have something in modern, like which we are not following the one which we followed previously. Is it not? Okay. So we understand the first question is, why do we go for classification of elements? We understand that will make us study the elements more efficiently, right? It is easier to study elements if at all we study them in groups rather than study them individually. That makes sense, right? And second thing is, if at all a new element is going to come, that element, how is it going to react? That also can be predicted. They will be able to predict the properties of the new elements to be found out with the help of classification. Right? So these are the reasons why we go for classification of elements, not because we don't have any other job, right? So it is going to make our study, it is going to make like the subject of chemistry study to be better. It is going to make it more efficient, right? Okay. So keeping all this in mind, right? Now we'll see who was the first. I mean, who was the first? I would say, I'll not say first one, right? Say one concrete effort were made. Like it's worth studying about it. So many scientists were doing it. Okay, so many scientists were trying to do it. But we are going to study only some handful of them, whichever were important, right? If at all you're still interested, you can just study, go into internet and you can study this in depth. Who are all the scientists, how and all they were doing it in the history. That all you can study. But in this chapter, we are going to study whichever is worth studying, right? Whatever was important, whichever made say some meaningful contribution to the scientific society, right? So those things only we are going to study. So under that, the first scientist who went for classification of these elements, this guy's name is what is called as Dobereiner. Okay, and what he did is Sir Dobereiner. Okay, so what he did is that he grouped elements, right? Whatever the elements which was known at his time. Okay, so he classified, he made the groups of elements into groups of 3 elements. Say group 1. Right, group 1 will have 1, 2, 3 elements. Group 2 will have 1, 2, 3 elements. Group 3 will again have 1, 2, 3 elements. So all his groups, this is one group, another group, this is group. So all the groups contain 3 elements each. Okay, right? So that is why his kind of classification, since he was doing it in terms of 3 elements in one group, right? So that particular way of classification is what is called as Dobereiner's triad. What is triad? Triad means group of 3. Triad means what? Group of 3. Right? So whatever the number of elements known was very less. So some 15-20 elements were only known at that time. Okay. So all the available 15-20 elements, he grouped them under groups of 3 elements each. Okay. Now on what basis he did this? Okay. What is the basis? Right? What is the basis for classification? Now, if I ask you, in the case of Dalton, what is the basis? The state of the element. In which state are they in? Whether they're in liquid state, solid state, or they're going to be in gaseous phase. That was the basis. That was the fundamental thing used in this kind of classification, right? So, like that, if at all we want to ask, what is the basis for the classification? What is the basis for classification in Dobereiner's triads? Okay, so or there's another way of calling it, right? What is the periodic function? Right? What is the periodic function which is used in Dobereiner's triads? What do you mean periodic function? Based on what function? Based on what particular thing you are classifying? Periodic means what? Repeating. Periodic means repeating. Right? How is it that this 1 and 2 are only put in 1, 2, and 3 are only put into the group? Right? But that particular fundamental thing is what is your periodic function? Based on what you went for classification. Right? Okay. So basically, these two questions are nonetheless same only. What is the periodic function or what is the basis for classification? So the answer to this question is that it is based on atomic mass. Okay, so not only this, the next few things, what are you going to see? For all of them, the periodic function or what is the basis for the classification is nothing but atomic mass of the element. Okay, now we know what is atomic mass now, people, right? Atomic mass. Can someone tell me what is atomic mass? What is atomic mass, people? Okay, fine. I don't like, see, there is a difference between mass number and atomic mass. They are different. Okay, mass number and atomic mass are different. Mass number is the number of protons plus number of neutrons. That is that we know. That is what is mass number. Atomic mass is the say, we should not say atom, mass of one atom. This is, remember that this is not mass of one atom. Okay. Right? Maybe I don't know whether you studied this in your 9th class. You might have studied. What do you mean by atomic mass? Atomic mass some way talks about the mass of the atom only, but not exactly. This is not mass of one atom as such, right? Because for example, I know, for example, say mass of sodium is 23 grams, right? Atomic mass of sodium is 23 grams, right? So that means, so if at all this was correct, that means it is the mass of one atom. That means what? One atom of sodium, very small atom. The atoms are very, very small, right? One atom of sodium is going to weigh 23 grams. No, that really doesn't make sense. Is it not? Because atoms are very small, right? How will something so small, subatomic level, right? How is it that it is going to have 23 grams? So it is not, okay? This is not mass of one atom. It is something else, okay? Maybe when you come to 11th class, right, I'll be able to give you a little more insight about what exactly is atomic mass. Okay, it is somehow talking about the mass of one atom only, but not directly. Okay, fine. So anyways, the periodic function which is used here is nothing but atomic mass. So in most of the cases, atomic mass and mass numbers will be same, right? And in some of the cases, it might not be same. Okay, atomic mass and mass number, first of all, their definitions are only different. They are not same value, they are not same things. But for certain elements, for certain elements, you will find them to be equal. For certain elements, you might not find them to be equal. Okay. Anyways, or actually, instead of keeping it for now, we will keep atomic mass and this thing as same only. Okay, for our discussions now, right? We are going to say that atomic mass is nothing but mass number, but it is not exactly like that. Okay. But we will we'll assume for the fact that atomic mass and mass number are indeed same. Okay, right, fine. So we understood that in Dauber-Innes triads, he used atomic mass as a basic function, right? Atomic mass as a periodic function. Okay, fine. Every element will have its own atomic mass and stuff, right? How exactly he did this, right? How exactly he did this? So what he did is that he put 3 elements in one group. Right, he put one triad. Say he put 3 elements in one group based on the fact I'm going to tell this. Okay, say what he did is, say if at all he took one group, right? Say I have whatever. Say I'll take one group was actually lithium, not lithium. Yeah, I think lithium is there. Okay, so one group was lithium, sodium, potassium. Okay, one group was lithium, sodium, and potassium. Right. So now, how is it that he is able to put these 3 elements in one group? Okay, so obviously use atomic masses, right? But how exactly atomic mass is used, you have to understand, right? So what he said is the 3 elements can be placed in one group if I take the atomic mass of the first element, right, and add it with the atomic mass of the third element. Right, and if I take the average of this, that is divided by 2, right, I should be getting the atomic mass of the second element. Okay, so basically, when I add the first element atomic mass and the third element atomic mass and divide it by 2, take the average of that, I should be getting the middle element is atomic mass. Okay, so whichever are able to fit into this particular category, right? First element, third element atomic mass combined, that is added, divided by 2. If I'm able to get the third element, second element is more atomic mass, right? Now those 3 elements can be put into one group. That's what he said. Okay, those 3 elements can be put into one group. And this is a very weird way of telling, right? Based on atomic mass, something you're taking average and you're getting this, and they're going to be placed in one group. But strangely, what happened is all 3 elements in this particular triad, right, in the group of 3, all of them were almost showing similar properties, similar physical, not physical, I would say similar chemical properties. Right, so even though this looks weird, I took the first element, say third element, I added the masses, divided by 2, and I got the element, second element as mass. Even though it looks weird, right, but this was actually proving that the elements which are there in the same group, that is your triad, right, they were indeed having similar chemical properties. Okay, right. So let us check whether it is going to happen for these. Okay, so atomic mass of lithium, let us check. right? So I think atomic mass of lithium is 9, huh? No, 6, right? Okay. So if I take atomic mass of lithium, right? So was 6, I think it is 6 only. Okay. Okay. Plus now I know the atomic mass of potassium. Atomic mass of potassium is 39, I guess. Right? Atomic mass of potassium is 39. Right? Okay, fine. So I think this was 7. Right? Yeah. Okay. So atomic mass of lithium is 7 and atomic mass of potassium is 39. Okay. So let us do the average. So 7 plus 39 divided by 2. Right? 7 plus 39 is 46. 46 divided by 2 is 23. And this 23 is nothing but the atomic mass of sodium. And the atomic mass of sodium is actually 23. Atomic mass of sodium is actually 23. So now you're understanding, right? If I take the first element atomic mass, third element is atomic mass, and I take the average out of it, you are going to get the middle element's atomic mass. Okay, right? So that was happening for a few of the trials. So see, he made so many trials. Okay, he made, as I say, I would have made almost like 5 trials, right? But not in all the 5 trials you are seeing, like he was able to prove that this was happening, in the sense that if I take the average of the first and third, I'm going to get the second element. It was happening only for very few of the trials, only 1 or 2 trials. First trial, this one was happening, right? Another triad he made was this chlorine, bromine, iodine, right? For this also it was working. Yeah, for this it was working. But there was a triad like this. There was magnesium, calcium, barium. Right now, for this triad, if they took the atomic mass of this and this and took the average, we were not getting the atomic mass of calcium. For this, it was not working. Okay, and there was another another triad which again is not working. Right, so only for few triads this particular thing was working. Right, this particular thing was working. That is our average. If we take, I'm getting the second element's atomic mass. But for majority of the groups, for majority of the triads, it was not working at all. Right, so that was his problem. Is it not? For some things, whatever he only explained, right? He only told that okay, if you take this, is going to work, and that is the reason why I'm putting them in the same group. That is the reason why I'm putting them in the same triad. But the entire whatever the basic thing, whatever you were based on that you are doing something, that itself is not working for some of the triad. Obviously, that you cannot accept it fully. Is it not? So rather, but still, he was able to do something. Like he was able to bring in some insight about classification. So that's why we're studying it. Okay, so this is what is called as Doberan's triad. So we understand that what are the demerits, right? What are the problems with this, right? First one was not all triads were following the law of triad. Okay, what is this law of triad? Right, this is what is law of triad. This point of time, that average of the atomic mass of first and third element should be equal to the atomic mass of second element. Okay, so that is the law he used. That is the law he proposed. Right, and that law of triad was not applicable for not all the triads, but for some of the triads only it was working. Okay, right. And second thing is, you will see this particular problem continuing in almost all the periodic table except for the modern periodic table, right? Except for the recent one. The problem which you're going to face is faced by all the other periodic tables, and that is the problem of isotopes. Right, that is the problem of isotopes. Right, we know what are isotopes. Isotopes will have same same mass number. No, it's same atomic number but different mass number. Sorry. Right, isotopes are going to have same atomic number but different mass number. Right, we know this, right? These are all isotopes. Okay, so for example, if I take hydrogen, right, I have hydrogen having atomic mass of 1, hydrogen having atomic mass of 2, and I can have hydrogen having atomic mass of 3. All these are hydrogen only. Right, now you understand that here here the periodic function which is getting used. The periodic function is what? Atomic mass. Atomic mass is the periodic function. Based on based on a mass number, or say based on atomic mass only, we are actually going for the classification, right? So if that's the case, these three should be getting three different places. Is it not, right? So this should have been in some group, this should be in another group, this should be in another group, because they have different mass numbers, different atomic masses, right? But we should not be doing it because they have similar chemical properties. They have similar properties only. Just because their mass is different, right, doesn't mean that their chemical properties or physical properties are different, right? But according to whatever the periodic function we are using, that is your mass number or atomic mass, right, they should be placed in different places, in the sense that they should be treated as different elements itself. Is it not? Because they are having different atomic masses, right? But we know that all of them are going to have similar properties, right? So definitely putting isotopes into the triads will again be a problem. Okay, because they are having different mass number, means they should have different places, but we know that they're going to have similar properties only. All are still hydrogen only, even though they have different mass numbers, they're still hydrogen only. They have same properties as hydrogen. All the three hydrogens will have similar properties, right? So two main problems we face, right? One is that obviously the law of triad, that average thing is not working for all the groups which we made, right? Second problem we'll face is about this isotopes. Okay, right? Any questions anybody has? Okay, fine. I hope you guys are following, right? So that was about the first attempt. Yeah, tell me, Kanna.
Understood, sir.
Okay, good, right? So that these are the things about your Dauber-Innes triads. Obviously, it had its own problem. Okay, fine. Moving on to the next attempt. Who made the next attempt in classifying elements, right? The second guy was Newland. Okay, right? Newland was a scientist, right, who attempted to make a classification for elements. Okay, right. So for in Newlands, again, your periodic function, that is what is the basis of its classification. The periodic function is again going to be atomic mass only. Okay, he also used only atomic mass as the periodic function, right? So again, whatever the problem we face, that is the problem of isotopes, right, will still exist in Newland's periodic table also, the Newland's classification also. Okay, we understood that it is atomic mass, but how exactly atomic mass, right? How exactly atomic mass was used, right, by Newland, right? So he gave something called as law of octaves, right? How you had law of triads, right? If you take the average of first and third, you're going to get the average, the atomic mass of second element, like that. That was the law of triad used by Dauber-Innes. Okay, so Newland gave something called as law of octaves. Okay, so people, these octaves are the, how to put it, the sounds you're going to come in your Carnatic music or any kind of musical instrument. That's sa, re, ga, ma, that's what we use. That you'll have 8 notes, right? Those are the notes in music. Okay, those are what are called as generally octaves. Okay, so we understand that like there'll be 7 notes, right? There'll be 7 notes, right? And the 8th note, sa, re, ga, ma, pa, da, ni, sa. Again, you see that the sa is repeating. Again, you will have re repeating like that. So what he said is, if elements are arranged, in the ascending order of atomic masses, right? Say starting with 1, 2, 3, 4, 5, 6, 7, 8, we are going to arrange the elements in the ascending order of their atomic masses. If we do that, right? If we do that, every 8th element will have similar properties. This is exactly what he told. Okay, if we arrange the elements in the ascending order of their atomic masses, every 8th element, how in music, every 8th note repeats, right? The sa is repeating, re is repeating, all these are repeating. Like that, every 8th element will show similar properties. Okay, so if at all if you want me to explain you how exactly this is happening, say I start with element atomic number 1, 2, 3, 4, 5, 6, right? 7, 8th element will come here. Again, 1 and 8 will have similar properties. Again, 2 and 9 will have similar properties. 3 and 10 will have similar properties. Like that, he said, right? So 7, you arrange them this thing, right? When you go to the 8th, the atomic mass of 8, now 1 and 8 will have similar properties. 2 and 9 will have similar properties. That's what he said. Okay, right? So that's exactly how he was able to do it. In your book, they would have given you what are the elements present in the same vertical column and stuff. You can look into it. Okay, so but what exactly is happening here? He arranged the elements in the ascending order of their atomic masses. Okay, and when he did that, he found out that every eighth element was having similar chemical properties and similar physical properties. Okay, and he found that out, and it was working quite well. It was working quite well. Okay, right. So what was the problem? Right, what was the problem here? Right, you can go look into the you can look into that particular table given in your textbook, like in your NCERT, it will be given how the table was looking. You're not Dobryna's, Newland's table was looking. You can look into it. But the basic thing is this. Okay, every eighth element was having similar chemical property. Okay, right. Again, there were some problems here. Right, there were problems here. What were the demerits? Right, so the demerits was again isotopes. Right, isotopes is a problem. Okay, now second thing is during his time, right, during this Newland's time, lot of new elements were getting discovered. Okay, lot of new elements were getting discovered. Okay, but there was no place for new elements. Right, if at all a new element is discovered, there was no place in this table, in this entire table, there was no place for the new element to be put in. Okay, right, so that was the second problem. Okay, there was no place for the new elements. Even if they are found out, the people didn't know where to put them in the Newland's periodic table, Newland's classification. They don't know under which you have to put it, right? Okay, because he didn't give you any space. All right, and the first problem was obviously the isotopes. Different isotopes should have different places, but we know all the isotopes will have similar properties only, so they should be in same place, right? Okay, so these two are the problems we face in Newland's periodic table, right? Or say Newland's way of classification. Okay, right, fine. And then came, so that was the second scientist. The first one was Dobryna, law of triad. The second one was Newland, law of octaves, right? And then came our, okay, fine. Actually, one more thing is, the one more problem we face with Newland is, he is not exactly a scientist, okay, right? He is not exactly a scientist. Actually, he was a musician. Okay, he was actually a musician who actually, this particular thing, whatever he told, right, did not have any scientific basis. Right, there was no scientific experiments which are there, which are going to prove this particular thing, whatever he said, but eventually it came out to be true. Right, it was eventually coming out to be true, but there was no scientific explanation for this, whatever the law of octaves he did. Okay, that was actually another problem. Okay, fine. Anyways, moving on to the next scientist who tried actually classifying these elements was Mendeleev. So we are going to study about Mendeleev's periodic table. Mendeleev's periodic table. Okay, right. Now this guy's table is very important. Okay, because based on Mendeleev's periodic table only, your modern periodic table is constructed. Okay, based on whatever the periodic table he gave. Okay, based on that only, your modern periodic table is there. But again, there are differences, right? There are going to be huge differences. Okay, fine. So again, in Mendeleev's periodic table, what is the periodic function? What is the periodic function? Right, the periodic function is going to be again atomic masses only. Right, just like in all the previous cases, that is in case of Dobryna or in case of Newland's, the periodic function. What is the basis for classification? The basis for classification is nothing but atomic mass again. Right. Okay. So he said the similar thing, right? He said the similar thing, what to say, what Newland said, right? If at all you arrange the elements in the ascending order of the atomic masses, every eighth element is going to repeat. He also said the same thing, right? But he did some chemical experiments and he was able to prove whatever you are saying. That is why it is very important. Okay, so the same thing as in the case of Newland, right? But he was able to, he's actually a scientist, he's a proper scientist, not a musician, but so he was able to conduct some proper experiments and actually prove the fact that indeed all the elements in that particular vertical line, every eighth element is actually indeed going to have similar chemical properties. Okay, so he was able to prove it. Okay, and one more beautiful thing what he did, right? One more major advantage over all other things we studied now. Till now we studied Newland's laws of octaves and Dobrynin's triads, right? So compared to that, this particular way of classification, whatever Mendeleev did, right, has a major advantage, one big advantage, right? What is that big advantage is that he gave space for new elements to be found out. Okay, that means what? He was actually thinking, okay, obviously these are not going to be the number of elements now. Definitely in the future, new elements would be found out. So I have to give some space. He was very, he was thinking for he had a very futuristic thought. Okay, so he, like in the last two periodic tables, that is the Dobereiner and Newlands, right, didn't have the space, right? They didn't have space for new elements to be found out. When the new elements were found out, people didn't know where to put them in their periodic tables. But Mendeleev actually gave some space for new elements to be found out. For example, like what some elements were there. Okay, 1, 2, 3, 4, 5, 5, 6, some whatever number, right? So after boron was there. Okay, under this he gave an empty space. Okay, after boron, this element was not found at that time. Okay, after boron, he gave one element. I mean, he gave a space, and he called that obviously this element is going to be found out. Okay, so he said that this element can be called as Eka boron. Okay, this element can be called as Eka. Eka means same. Okay, in Greek, right? Eka means same. So obviously this and this element is going to have similar properties. Okay, so he said that there will be one element you will find in the future, right? You will find in the future that is actually going to have properties similar to that of boron. That's why he said Eka boron. Okay, and he actually after this element was found out, okay, this element was actually found out to be aluminium. Okay, this element was found to be aluminium. Again, this place was empty, and he was still alive when aluminium was found out. Okay, he was still alive when aluminium was discovered. Okay, so then they removed this place of Eka boron and aluminium came into this place. And after that also some empty places were there. Okay, and then he called it as Eka aluminium because it is going to behave as if it is aluminium. Same, like similar kind of properties. Okay, and again, this after his death, this particular element was found out, and then that element was found to be germanium. Similar properties. Okay, so another thing was also happening. So in one group he had carbon, silicon was there. Okay, carbon, silicon, they were all following this, whatever the every eighth element is following the same property and stuff. Right. Again, after silicon, he gave an empty space. Okay. Oh, I'm sorry. This is not germanium, people. This was gallium. So sorry. Okay, this was nothing but gallium. Okay, not germanium. Sorry. Okay, and then then obviously he had an empty space after silicon, and he called this one as Eka silicon. That is a property. I mean, the element is going to be discovered in the future, which will have similar properties like that of silicon. He said, and obviously this element was in the future it was found out to be germanium. Okay, germanium was the element, which is nothing but which was called before even it was found out, right? It was named by your Mendeleev as Eka silicon, and eventually it was found out to be germanium. They named it as germanium. The element was discovered. Okay, so this was a very very huge step in the classification. He was able to predict, okay, this element will be found out, right? And this is going to have similar properties like this element only. And he even he was even given a, he even given a name for the particular element. He gave a space for the new element to be found out. A very, very important thing which happened only in modern, only in Mendeleev's periodic table. The other two periodic tables were not able to do this. Okay, a very huge improvement compared to the other two periodic tables. Okay, right. But still it has some problems. Okay, but still it has some problems. Okay, what was the problems? What are the demerits he faced? We face. What were the disadvantages we face with the Mendeleev's periodic table? Right. Again, the problem of isotopes is still existing because he was still using atomic mass only as the periodic function. So that is again a problem. Right. Now, second thing is, right, so we are actually arranging the elements in their ascending order of periodic table, is it not? Right, they are ascending order of periodic tables. So what he did is I think it was cobalt and nickel, or say I think it is nickel and copper. No, it's cobalt and nickel only. Okay, so if you check cobalt and nickel, right, so you understand, nickel is actually having more atomic mass compared to cobalt. Okay, the atomic mass, if I compare, nickel has more atomic mass than cobalt. Okay, I don't know the exact, I forgot the exact number, but understand that nickel is actually having more atomic mass than cobalt. Okay, so when I arrange this like this, first cobalt should come, then only nickel should come, because nickel is having higher number. Ascending order we are going. First cobalt should come, then only nickel should come. Right, but what happened is there were elements above this, below this, and all. So obviously the elements which are there in the same vertical this thing should be having similar properties. That's what he said, isn't it? Right, whichever is coming in the same vertical column should have similar properties, because that is how we arrange it. Right, but just they were not having similar properties. Okay, this particular group and this particular group was not having similar properties. So but what he did is, when he kept nickel first and then cobalt, and above elements, below elements, then they were having similar properties. That was what. Okay, again I repeat, right? So nickel should come next. Cobalt should come first, then only nickel should come according to the atomic mass. Right, but if I arrange them properly, if I arrange them like that, the elements that are there which are coming in the same same vertical column, right, they were not having similar properties. Okay, but when he arranged the elements like this, first when he kept nickel and then he kept cobalt, then the elements are coming up and below, whatever they had similar properties. Right, and he had no explanation for this. Right, he had no explanation for why is this happening like this. Right, nickel comes first, then cobalt, then they're having similar properties. But you said only ascending order. Why are you not following ascending order? When he asked the question, he was not able to answer. Okay, so the next problem is ascending order. Ascending order is not exactly followed, is not sometimes followed. And there was no explanation for this. Why is it not followed? So he just said, they have similar properties, that's why I'm doing it. But why exactly it is happening? He doesn't know, right? He didn't know at that time. Right, so the ascending order he was mentioning was sometimes not followed. For example with cobalt and nickel. Okay, right, so these were the problems we face with your Mendeleev's periodic table. But the major advantage is this, that he gave spaces for new elements to be found out. Eka boron, Eka silicon, Eka aluminum. Right, you have to remember the names and what their elements were eventually found out to be. Right, everything you have to understand. Right, so people, I think we'll stop this for today. Yes, Kana, any doubts?
Yes, sir. Cobalt and nickel part I don't understand, sir, because in the textbook, sir, it is like cobalt has 58.93 and nickel is having 58.71, sir. I did not understand.
58.93 and 58.71. 58.93 for this thing, 58.71 for cobalt. Okay, now you understand, right? Huh?
Sir, it's opposite. Sir, 58.93 is cobalt and 58.71 is for nickel.
Okay, fine. 58.93. Okay, so then I think what again, I think I told the exact opposite. Okay, so what you have to understand is, so you understand that cobalt is actually having more atomic mass than that of nickel. You understand that, right? This is 58.93, this is 58.71. Okay, cobalt is having more atomic mass than nickel. Right, so when we go for the ascending order, 1, 2, 3, 4, something like this. So whenever this number comes, right, whenever this number comes, we have to put what? We have to put first nickel, then cobalt. And above that, some elements will be there in the group, and same goes with the cobalt. Some elements will be here, some elements will be here above or below cobalt, right? So, I mean, the elements are going to come in the similar group, in the same vertical column. They should have similar properties. That was the whole idea, isn't it? Every 8th element was coming in the same, falling into the same line, same vertical line, and whichever comes in the same vertical line will have similar properties. Okay, so when we go for ascending order, first nickel should come, then only cobalt. I told it was wrong here. Okay, I told it wrong, right? So first nickel should come, then cobalt should come. But just because they were not fitting into the properties, right? The elements above and below, they were, right? The properties of them which were not matching with that of cobalt and nickel, in the sense that the elements which are here, X, Y, Z, and all that. So where the properties of them were not matching with nickel. Same way, say I had some element A, B, C, and stuff, their elements property were not matching with cobalt. Okay, so to overcome this problem, what he did is, instead of putting nickel then cobalt, he kept cobalt and then nickel. So, and when he did this, he was able to match their properties. The element X and Y and Z and all were actually having properties similar to cobalt, and the elements A, B, C, whatever, they were having similar properties to nickel. Right? So even though he was not strictly following the ascending order, that's what I'm trying to say. The ascending order should be nickel first and then cobalt, right? But they were not fitting into the similar properties. So he changed it. He put cobalt first and then he put nickel. Right? And then he was not able to give any explanation also. Why is it happening like this? Right? He said that I'm changing this because I'm having similar chemical properties for the same element in the particular vertical line. But why exactly he's doing it? Why is there a change in the chemical property with respect to atomic mass? Nothing was able to mention. Nothing was able to explain. Right? So again, that's what I'm saying. The ascending order is not sometimes followed properly. For example, for cobalt and nickel. Now you did understand, Kanna? Is it okay?
Yes, sir. Understood,
Okay.
sir. Thank you.
Right. Okay. Anybody say any other questions? Okay, so that is about your mental history periodic table. So tomorrow's class will be not tomorrow's class, next week's class will be starting with your modern periodic table. Okay, fine people, let me stop here. There was something in the chat. Sir, there were 3 triads, right? Can you repeat those?
Sir, I got it, sir. I got it.
Okay, fine, Harita, good. Right, okay. Let me stop sharing. Okay, people, thank you so much. We'll again meet next week. I'm ending the class.
Thank you, sir.
Thank you.